This is an AP recording of bonding in solids. We have here a textbook table showing the 4 types of solids that we can encounter in chemistry: the molecular, the covalent network, the ionic, and the metallic. We'll be talking about all 4 of these types. The forces between the particles, which may be atoms, they may be ions, they may be molecules. The molecular forces are London dispersion forces, dipole-dipole forces, and hydrogen bonds. In the covalent network, we'll see a large network of covalent bonds. In the ionic, we will see that positive and negative ions are attracting each other electrostatically. And in the metallic, we'll see something called a metallic bond, which really is in kind of a diffuse bonding between electrons that are very, very highly mobile and the nuclei of the metals that they are kind of immersed in. In molecular solids, we have intermolecular forces. Remember, we are talking about forces not within the molecule, which are covalent bonds, but between one molecule and the next molecule. These intermolecular forces can be very weak, like the London dispersion forces, stronger, dipole-dipole forces, or hydrogen bonds. Weak intermolecular forces are going to give rise to low melting points. The stronger the intermolecular force, the higher the melting point. We've seen in first-year chemistry that, for instance, the hydrogen bonding, which is relatively strong, gives water an unexpectedly high melting and boiling point when you consider the hydrides of the group 6 elements on the periodic table. It's a lot higher than it ought to be. Room temperature gases and liquids are going to usually form molecular solids at low temperatures. Now, efficient packing of the molecules is important. What this means is they're going to assume a low energy state. The molecules themselves are not regular spheres, as for instance we see in ionic substances, binary substances like sodium chloride. And so the molecules are going to fit together kind of like pieces of a crossword puzzle. Now, the covalent network solids are forces that hold atoms together in large networks. For example, a diamond is held together by covalent bonds in a network. Graphite, like the graphite in your pencil, quartz and silicon carbide and boron nitride are all held together by very, very extensive networks of covalent bonds. In diamonds, each carbon atom is bonded to 4 other carbon atoms that are tetrahedrally spaced around it. So there's a 3-dimensional array of atoms. And unless you've got a significant occlusion in the crystal, fault, if you will, fault line, the diamond is very hard, and it has a very high melting point between 3,000 and 4,000 degrees Celsius. This gives you an idea of what we're talking about. The diamond, as you can see, each one of the carbon atoms is bonded to 1, 2, 3, 4 nearby carbon atoms. And those carbon atoms then, those covalent bonds like this one and this one and this one and this one, are strong, and they work 3-dimensionally to hold it together. We'll see that graphite, on the other hand, is a series of sheets of carbon-carbon covalently bonded atoms that are loosely connected sheet to sheet. In graphite, each carbon atom is arranged in a planar hexagonal ring, such as you saw in the previous slide. The layers of interconnected rings are placed on top of each other. As you can see on the right here, this interconnected network of rings is on top of this one. The distance between the carbon atoms is close to that of benzene, inside the ring, but the distance between the layers of sheets is fairly large. The electrons are moving in delocalized pi orbitals. In other words, we're looking at pi bonding between the sheets here. These are overlapping p orbitals. And since they're delocalized, graphite is a good conductor of electricity. And we'll see later on we'll actually use that in a lab. The pi orbitals also, since it's a weak bond, act as a kind of a lubricant between the sheets. And so graphite is frequently used to lubricate in cases where oil is not a good option. So that's graphite. Graphite is converted to diamond at 3000 Kelvin and 150,000 atmospheres of pressure. It's necessary to break up that flat lattice and change the pi bonds so that instead of sp2 hybridization, we have sp3 hybridization all around the carbon. Now, silicon is a covalent network solid. You might imagine that because it's in the same group as the carbon. It is a semiconductor. Silicon is going to form a three-dimensional network similar to that of the diamond. Its conductivity is going to increase as the temperature increases because the electrons become more and more delocalized. Now, you can use the periodic table to understand why we can change the electrical properties of silicon. If we were to dope, or if you will dissolve, a little bit of an element that has one extra valence electron over and above silicon, in other words, it has 5 valence electrons instead of 4, we have what we call an N-type semiconducting material. It has a negative charge capacity. We can also take a different sample of silicon and dissolve an element with one less valence electron, 3 valence electrons in it, and this converts silicon into a positive charge carrying material. We can put N-doped and P-doped materials together to control electron flow. We'll show an example of that. As you can see here, we take silicon, and if we've got antimony in between the silicon atoms, there is one more electron in the outer shell of the antimony than there is in the silicon, and so electrons can flow more freely here. Whereas if we dope it with boron, the silicon now has a kind of an electron hole here where it's missing the electron that you would expect, and electrons then can flow towards this particular semiconductor. Electrons are only going to flow out of the antimony-doped silicon and only going to flow into the boron-doped silicon. So in an N-type semiconductor, we can have electrons that are going to flow in the direction of, for instance, a P-type semiconductor. So the electrons are in excess here and deficient here, and we will get current flowing only in one direction, from the N to the P. Now, ionic solids. Pretty straightforward. The ions are spherical and they're held together by electrostatic forces plus to minus attraction. There are some simple classifications for ionic lattice types that used to be things you had to memorize for the AP exam. Fortunately, you don't have to do that anymore. However, you must know that ionic solids are held together electrostatically. Metallic solids offer a problem. What we see in terms of the bonds is too strong for the London dispersion forces, and there are not enough electrons, say in sodium, to create a covalent bond. So what they're saying is that the metal nuclei are in a sense floating in a sea of electrons. Metals conduct electricity and heat because the electrons are delocalized. They're not attached to any particular nucleus, and of course they can move around a lot. This is an example that will show us why metallic solids bend and conduct heat and electricity. The electron C can move. These electrons are not attached to that particular nucleus or this one. They're attracted to all of the nuclei. And if we put a potential difference across this wire, we can see that if we supply electrons here, they're going to move into this electron C. And if we have a positive charge here, they'll be attracted out in that direction, and we can get an electric current. Alloys, our last topic, are metallic mixtures. They contain a mixture of elements. Now, they don't have to have only metals in them. Some substitutional alloys are those where the host metallic atoms are replaced by other metal atoms. So, for instance, in brass, we add 35% or a different amount of zinc to copper, and it gives us a little harder alloy. Interstitial alloys, on the other hand, have much less in the way of mixed-in elements, and they very frequently are nonmetals like carbon or sulfur. In carbon steel, a small amount of carbon is left in the steel, and it makes the iron harder than it ordinarily would be. So that's alloys, which are mixtures of a metal with another element.